Hey there, I've got another practice physics GRE problem for you. This one is number 70 on the 1992 practice physics GRE. It's a relativity problem. Number 70, a monoenergetic beam consists of unstable particles with total energies 100 times their rest energy. If the particles have rest mass m, their momentum is most nearly A mc, B 10 mc, C 70 mc, D 100 mc, E 10 to the 4th mc. So that quick glance at the answers doesn't really help me that much because they're all the same units, obviously. They all have units of momentum. It's just some constant. So I got to know what I'm doing here, and I don't think it's safe to say that you can just intuit an answer out of this. I don't know, maybe you can, I can't. So the equation that I want to use for this one, and the equation that is used in a lot of the physics GRE relativity problems, is the relativistic energy equation. So when I say that, does an equation pop into your head? Can you write it down really fast? If you can't, I got a quick way to help you remember that. It's just, okay, so the total relativistic energy, E squared, equals PC squared, where P is the momentum, C is of course the speed of light, plus the rest mass, m naught, C squared, quantity squared. So that's the relativistic energy equation. That one should pop into your head really quickly when you're talking about doing relativity problems, because they use that a lot in the physics GRE. There's a little visualization that may help you. It kind of helps me. I didn't hear this from anybody, I just came up with it. But for me, since I am kind of visual, for some reason this helps me, because it's kind of like a right triangle, the Pythagorean relationship. I don't know if that helps you remember this equation, but if it does, go with it. If not, just forget about it. But there you go. When I see that triangle in my head, and I remember these things, E as the hypotenuse, PC, you know, like a computer PC, and then m naught c squared is kind of like mc squared with the rest mass there. And then I remember to square all of these things because it's a Pythagorean triangle. When I look at that, that's what I think. So, if that, like I said, if that helps you use it. If not, meh. Okay, one thing they do in this problem to try and throw you off is they won't use m naught like you'd like to use. They want to use m for the rest mass. Okay, so fine. Have it your way, physics GRE. We'll use m for the rest mass, knowing full well that if we're going to look for like the relativistic mass, we'd have to call that m prime or something, right? We don't really need that in this problem, though. It's just an annoying little thing that they do. So what they give us at the beginning is that this is actually E equals 100 times, so that the energy at that relativistic speed is 100 times the energy at rest, so E sub r. And I think you can see from the equation, I don't really want to write it, but the rest energy, when this term goes to 0, the momentum goes to 0 when the particle's at rest, right? So this just drops out, and you get the rest energy, E sub r, just equals this term, with m being the rest mass, times c squared, and then you can take the square root of that. I mean, I don't want to do the extra step, but it's that and then all of this squared, right? I did the extra step anyways. Okay, so that's all the rest mass is. And then, so what we're saying is that the total energy is 100 times that. So 100 mc squared. And so we can just plug in this into there and run with it. And it works pretty well. There's other ways to do this problem. I've seen other solutions to this, but you know, this I think makes a lot of sense, and you get there pretty easily. So oops. Oh, no, that is right. Yeah, the whole thing has to be squared. Okay, equals PC squared plus MC squared. Alright, so we get 100 squared. I don't even have to write that out yet. Well, yeah, I will. So 10,000 m squared c to the fourth. Now I'm going to bring this over, minus just 1 m squared c to the fourth equals p squared c squared. Let's do that. I can divide a c squared through, and that's going to clear out, and I can combine these together, so I get 9,999 m squared c squared equals p squared. So I combine those and divide it by a c squared. And then that's what my p squared is. So my p equals the square root of that junk. Square root 9,999 mc, because I took the square root through all that. And then for computational purposes, of course, that's painfully close to 10,000. And that equals 100 mc. And notice in the answers they did give you a couple of trick answers in there. E is 10 to the fourth, so if you were sloppy and forgot to take that last square root, you could fall for that one. B is 10, which I suppose you could get there somehow too. The right answer we want, though, we're going to be looking at D, which is P is equal to 100 mc. Alright, so that's that. A fairly easy relativity problem solved using the relativistic energy equation. So thanks for watching. Study hard. See you next time.